Starting, and Hua today is going to present us about zero duality gap conditions via abstract convexity. Hua is moving from place to place, crisscrossing Australia from east to west. Now she is in Perth because it is probably safer there at the moment. She still keeps doing things which she started in Ballarat, which is a good thing. And it's another good thing that the topic also involves South Australia. So Hua is trying to merge all our optimization forces together in this presentation. This is great. For those who don't know Hua well, she completed her PhD very recently, and now she's going to teach us a little bit about zero duality gap conditions. It's partially optimization and partially pure mathematics, abstract convexity. Okay, Hua, the ball is yours. Go ahead. Mute myself and go ahead.
You have to mute yourself first. Thank you very much for your nice introduction, and hello everyone. Good afternoon everyone from Australia, Vietnam, Asian country, and also good morning from anyone from European countries, and evening from anyone who from North and South America. So my talk today is a joint work with Regina, Alex, and David. This is about abstract convexity, and zero duality gap is an illustration, and also some application of abstract convexity. So abstract convexity is originates from a very fundamental fact from standard convex analysis, which is a convex functions is the upper envelope of a collection of affine functions. Of a collection of affine functions. So here we have so many key results in convex analysis. Okay, so many key results in convex analysis is actually from two key factors. The first one is the supremum operators, and the second factor is the set where the supremum operators is taken over. So this is the set. So let's take a very simple example. This is a x squared, and everyone knows that this is a convex set, convex functions. So this is a support affine functions of x squared. So this is a set of support affine functions. So in the photo, in the figure here, this is on the blue line, support the red curve here from below. Okay, this is one dimensional functions, and this is a space of all the affine functions. This is very elementary. Okay, what about if I consider functions which is not convex? So this is a not convex functions, and certainly you couldn't approximate the whole graph with a linear functions, linear affine functions. So that is, so in the next, so but however, instead of approximate by the linear functions, we can approximate by quadratic functions. So this is tell us the idea of abstract convexity. So so the idea of abstract convexity is we still keep the supremum operators, but instead we change the set here. Instead, we take in the supremum over a set of affine functions. We change affine function to some other elementary functions. In this example, the elementary functions are quadratic functions. So here, so the affine space here is comprised all the functions. We change the linear functions here, t here, by a quadratic functions, and we have the same dimensions, another this space H here is called abstract affine space, and this has the same dimension with the small with the other space H here. So the outline of the talk today is first of all, I'm going to talk about abstract convex functions, definitions, and all the basics properties. And the next sections, I'm going to talk about some calculus rule and probably just some rules. And the next one, using the sum rule, we derive the zero duality gap. And the next sections, I'm going to talk a non-trivial example where all the analysis work. And in the section sum rule here, this is the very first time we consider a topology. This is topology, which is the generalizations of Weak-Star topology in a dual space in the standard convex analysis. Okay. So this is the definitions of abstract linear functions. So the abstract linear function is actually just some collection of functions, of the real functions that satisfy certain property. So certain property, it depends on our purpose. We can impose some property we want. Keep in mind that the set X here is just a non-empty set. We don't need any linear structure or any topology on X at the moment. And F here is the set of all the functions. And then in this study, we consider two very mild assumptions. The first assumption is this set L here must close with respect to the addition operators, which is very natural. And the second assumption is every element of the abstract linear function space must be decomposable. So keep in mind that now the set L here is not yet a vector space. It just we just have the addition operator. So if 0 belongs to the set L here, then the space L here with verify A will verify B as well. Because obviously, if we have L here is equal L plus 0, so it's always decomposable. So in the okay, if we have a space of abstract linear functions, then we can certainly define a space of abstract affine functions by taking all the abstract linear functions and we add the vertical shift. So this is L here is a linear functions, and then we add a arbitrarily vertical shift, and then we have a space of affine functions. And then the suppose set of functions is a collection of all the affine functions that doesn't exceed the value of the function f at any point in X. So this is very the generalization is very straightforward at this point. And a function f is H convex if there is a subset of affine functions, so that the function f here is a supremum of all these functions. So let's think about H here is an element functions. Okay, so now there are many key terminology notions in standard convex analysis can be extended to the framework of abstract convexity. For example, infinite convolution. Okay, infinite convolution is actually not generalizations. It's just a standard definitions. But if you look at here, this is a summation of the value of the functions in image space, which is okay. But if we look at here, this is a summation of all the element in the set L. So that's the reason why we need the first assumption that the addition operator must be closed, and the second assumption on the space that it must be decomposable. Because otherwise, it's not decomposable. This set gonna be empty, and we don't want to take infimum over an empty set. So that's the reason why we impose the two conditions. And the next terminology is Frances conjugate. it is also straightforward. If you replace Lx here in the standard convex analysis, you have x star x. So this is a standard definition of French conjugate. And for subdifferentials, the same things. So subdifferentials is all the okay. For these definitions, if we replace this one as this one is x star y, and then x star minus x star x, we're gonna have x star y minus x. So this is become a very standard definition in convex analysis as well. So the generalizations are very straightforward. So what next? So with just these simple assumptions and simple generalizations, we can, there are many properties can be preserved in the framework of abstract convexity. The first one is, and I think the most interesting one is a global property of convex analysis is still preserved. The main reason here is because we keep the supremum operator. So if f attains global minimum at the point x bar, then 0 belongs to the subdifferential set at the point x bar. And another basic property is that the supremum of the support on the function in the support set is obviously less than the function itself. And the next property is generalizations of French inequality. So the French conjugate of a French conjugate is less than the function itself, and the equality holds if the function f is a H convex functions. And then we have this inequality, so which is the conjugate of the sum is less than the infimum convolution of a conjugates. And then the third one is a sum rule. So for this sum rule, we don't have the exact equality here. We only have the inclusion of the sum of subdifferential and with the subdifferential of the sum. So these are very basic property of abstract convex functions. How about abstract convex set? So for abstract convex set, a set C belong to the space L. If for any point outside that set, there is an element X in the primal space. So X here, let's think of it as a primal space, so that this strict inequality hold. So let's take this simple figure. So C here is a set, is L convex set, and then L0 is a point outside the set. So this line here represents the element X belong to X, so that this line X here separate the point L0 and the set C. So this definition of abstract convex set has another equivalent definitions, which are related to abstract convex functions. So the set the set C is L convex if and only if there is an L convex functions, so that the set C here is the support set of F in L. So we take all the functions in L support the function F, and this is going to be the set. This is going to be equal the set C, even only if C is a L convex set. Okay, so next we move to some simple example. So let's think about the example at the beginning of the talk. This is the example is about the collection of all the linear functions is a quadratic functions with the scale. And then a abstract affine functions is other functions is a quadratic functions plus a vertical shift. Like let's take this set with the set in the abstract affine space functions, abstract affine function space. Then we have this phi AB. This is the parameters is AB. This is actually equal AT squared plus B. For such that B less or equal 1 on A, then this set is actually the support set of a functions fx equal minus 2 absolute value of x. So this tells us that this set C here is a H convex function, H convex set. So let's draw that some figure to have intuition. So this is the function minus 2 absolute value of x. So this is all the support quadratic function of the functions of these functions. Okay, and then we can easily calculate the subdifferential and the differential conjugate of function f. And okay, let's check this calculation. The subdifferential of the function f at x when x equals 0 is empty. Let's check the figure again. So if you check here at x equals 0, you will see that there's actually no function, no quadratic functions can assist that point, can support this point. That is the reason why we have the subdifferential of the function at this point is empty. But if you pick another x, for example, this one, we will have a curve that support this function, and that is the. And then we scale that up, and then we have this is the French's conjugate. No, sorry, the subdifferential at that point, and it's only one quadratic function support that function at this point. Okay, so a small example, and this example is for Vera. So, so whether or not we can go for higher dimensions. So if our example is in one dimension function, which is very elementary. So of course, we can go beyond one dimension to n dimensions, like the set abstract linear functions is the function of this type. So if I don't consider the quadratic term here, this is standard linear functions. But if I consider the quadratics, and this is similar to the example we have in one dimensions, and then we also have this set as a abstract affine functions. There's another interesting class of abstract linear affine, abstract linear functions. So if I consider the linear space is all the function of this type. So which means that here we have the L here is the vector space with all the basics here is put n plus 1 basics, which is h0, h1, and hn. With h1 and hn are basics of Rn, and then h0 is the quadratic is a square of the norm of the vector x. So then we have this space L has a dimension n plus 1, and then its R5 space has a dimension of n plus 2, and then all the lower semi-continuous functions, which is bounded from below, become a H convex, which would tell us that if we go beyond one dimensions, our abstract linear space become too large, and that make all the functions become H convex, and this is not a good thing because we consider the space too large. So anyway, so we move to another sections, which is the calculus rules, because we need the rule we need some rule to calculate the subdifferential. And the calculus rule I'm considering here is the sum rule, which plays a key role in many in convex analysis. So let's recall this sum rule from the beginning, from the basics property. We desire to have this one as equality, not inclusion like this. Then how we have this equality? It's not always, we not always have equality all the times, but under some assumption we may have. So we have a result from in 2000s of Cesar Kema, which is saying that if under these conditions, which is the epigraph of a conjugate, the sum of epigraph of conjugates is the epigraph of the conjugate of the sum. And then if these conditions hold, and this is equivalent to the condition that this equality, we have the equality hold, and not even, and this is even better, that we don't need even the term eta bigger than 0 here. We don't need the intersection here. We can omit that. We can make eta equals 0. So which is a very strong calculus rule we have. But unfortunately, with these conditions not even hold for every standard convex functions in a classical convex analysis. Indeed, this conditions is equivalent to the equality of the of these two. And keep in mind that from the beginning we have this one is sorry, I couldn't write on the screen anymore. Anyway, so I don't know why. So anyway, so for this equality, we don't have this equality in general. Indeed, from the basics property, we have the equality, the inequality that the infimo here is bigger than the conjugate of the sum. And what the addition condition that we must have the exact infimo, which means that this one have a solution would have an x that infimo 10. So if we go back to what we have in standard convex case, why not? In the standard convex case, we have this one. So we have this one is the standard convex sum rule. So we have, what do we missing here is a weak star close of this set. So at the moment we don't have any topology to work on. That is understandable why we couldn't have a proper sum rule, a good sum rule. So that is why we impose a topologies on the set L. So if if we go back to the set of the functions, on the real functions, we have the weak star topology, which is the weakest topology that make all the functions here continuous. So in the dual space, if we restrict this topology in the dual space, it's become a standard weak star topology in X star. And then we equip that topology, embedded this topology in L by just restrict this topology in L. But we should have that the L here, the set L here should be closed with respect to that topology. So we call that topology is pointwise convergent topology because of this property. Because of this property, make all these functions X here continuous. And then we also at this from the section forward, we also assume that the space L is a vector space. And then with these two assumptions, we have L is actually a locally convex space. So with this property, with this topology, what do we have? What the properties we have? And keep in mind that this is the very first time we study a topology in the abstract convex space. Okay, so we have all the functions. X here is continuous, which is obviously from a definition. And also the conjugates of the conjugate functions is lower semi-continuous. And all the L convex set and the H convex sets are closed with respect to that topology. And also all the subdifferentials are closed as well. And then how about the sum rule? So do we have yet the equality yet? So the answer is still no. We still have this inclusion. But keep in mind that this set is already bigger than the set before, so we almost there. And also, so the reason why one of the most important reasons why we study we start topology in X star is that because of the Banach-Alaoglu theorem, which said that on the unit ball in X star is we star compact in the we star topology, and then we have the similar result, similar extensions here. So the set A here is on the function f, so that f is between G and F. The G and F here are the real value functions. Okay, I can try again. So, okay, so if from these assertions, we can cover the standard Banach-Alaoglu theorem. If we take G here as minus X, norm of X, and F is the norm of X, then this set is obviously we start compact. So we have all of this property. Then the question is, oh, how about the sum rule? So do we yet have the sum rule? Okay, so although we don't have the sum rule here, so we still have a inclusion here. But under my assumption, we will have the equality. So the assumption we are using here is we actually extend from the sum rule of Caesar-Kema and his co-authors for this. So for his assumption, for the assumption in that sum rule is that this is just the epigraph of the F star at addition with the epigraph of G star equal epigraph of F and G star. But here we have a weaker assumption that the closure of this set equal this set. So the set here doesn't need to equal, but the closure is equal to that epigraph. And okay, and these conditions hold for every lower semi-continuous functions in standard convex case, which means that we cover the standard convex case. And then if for any functions, if this condition hold, we will have the conditions for the sum rule. And this sum rule is in the convex case, it is standard sum rule. Yeah, it is sum rule, is a no sum rule we are using in convex analysis. Okay, so we have the sum rule. So we have topology, we have all the key properties. So now we use all these properties to derive the zero duality gap conditions in the in the framework of nonconvex functions, because now our functions f here doesn't need to be our function f here doesn't need to be convex anymore. It can be any functions. So the minimization problem is a minimize of the sum of m functions. So this minimizations has a dual form as follows. It's a supremum of all the minus conjugate of with L1 plus summation of L1 to Lm is equals 0. Okay, so this is a dual problem of P, and Vp and Vds are the optimal value of P and D respectively. And then the zero zero duality gap holds if the two values equal each other. So keep in mind that we always have the optimal value of D is a lower bound of E, but we are not lower bound E, but we are not sure that the E equality hold or not. So if we, so the ideas of having the zero duality gap conditions is we are employing the idea of infinite convolutions. The reason is if we have VB here is actually the value of the conjugate of the sum at 0, and also the VD here is the optimal value of the dual functions is the value of this function at 0 as well. So equivalently, recall that from the first sections we have this equality. Inequality. That explains why we have VD is a lower bound of VP. So naturally, we have the zero duality gap is equivalent to these conditions. So this equality. So these two functions here equal each other at the point 0. So this idea is actually from Borwein, Regina, and Yao in 2014. So they derive the characterizations for, instead of this equality, they derive for this equality. So obviously this equality implies this equality. So what do we have for abstract convexity? So keep in mind that even the function fi here is not necessary to be convex. So even H convex. So we don't care about this any property of the functions fi. And so if we consider the following 5 conditions, so the first condition is the condition we want to characterize. This is the equality of the two functions in L. And the next one is actually the sum rule. But the sum rule here is, if we recall again the sum, this equality here. So if we recall again and this sum rule doesn't involve closure of a topology. If we recall again the sum rule of Zeta-Schema, we don't have this term. That is why the sum rule is equivalent to this equality, but with the condition that the convolution attain the minimum is exact. So for this condition, we don't need the convolution exact. So the three, then we consider the next 3 property. So this properties is a relation between the subdifferential of the sum and the subdifferential of sum and the sum of subdifferential as well. But notice that with the subdifferential of the sum, we scale that epsilon a little bit bigger, so that to make this set is a little bit bigger, so that it's and even if we make it bigger to contain this subdifferential of the sum. So the next 2 properties involve topology. So the next one is a closure of a sum of subdifferential, and the next one is a semi-continuity of these functions. So in general, without any further addition assumption, we will have the first 3 properties are equivalent to each other. So these 3 properties that doesn't involve topology equivalent to each other. But for the next 2, we have 3 imply 4, 4 imply 5. Okay. But if we have the sum rule hold, then all 5 statements are equivalent. So this will recover the result in standard convex analysis, because we have the sum rule here hold for every log semi-continuous functions. Okay, So if we go back again, so what we do with what we try to characterize is not the zero duality gap, but this equality in L. And this is a little bit stronger than zero duality gap as we discussed before, because we only need this condition hold for just at 0. So that is why we extend this one. So we just characterize this equality only. So this equality is equivalent to zero duality gap, and this equality equivalent to these conditions. So this is the very first time we have a necessary and sufficient conditions for zero duality gap. And I think this one is even new for convex analysis, for standard convex analysis. What is saying here is, what is saying in these conditions here is, for any epsilon, there exists an x so that 0 will belong to this sum of subdifferential. And you may think that whether x depend on epsilon or not, the answer is yes, x depend on epsilon. So keep in mind that at the moment we still have x here, doesn't need any topology or vector structure. So, but if x has a topology, for example, and then do we have all the collection of all the x with respect to all these epsilon? In that topology, is there anything special about that? Does they have a cluster point? So the answer is no as well. So, but if they have a cluster point, then we actually can get rid of epsilon. So we can have an x for any epsilon. So if this is the case, then for any x, for there is an x, so that this inclusion hold for any epsilon, and this will imply this one, of course, but the other way around hold true as well, that if x here will be a solution of the problem B, and also the convolution here is exact. So we have B are equivalent to each other if the with the condition that the convolution here is exact. So we have two sufficient and necessary conditions out of this characterizations of this idea. So okay, so we already finished the first sections. So we move to a very simple example. So this example is based on one dimension functions, so that there will have a lot of beautiful figures, because I can draw one dimension functions. So so let's go back to the example from the very beginning. So we have the space of abstract limiting functions are quadratic functions, and then we add the vertical shift. We have the abstract affine functions. And what good about this space? So we managed to prove that the sum rule holds. So the way we prove the sum rule holds for this non-trivial example is that we, instead of prove the sum rule alone, because it's a little bit complicated, we prove this equality instead. So so what is interesting, what is important about this equality? So if we think about so in able to prove this equality, we prove that the closure of the sum of two support sets is a H convex set. So if we think about a standard convex case, we have two closed convex sets and we add them together, and this is still a convex set, but we are not sure that they are close or not, and that is the reason why the sum of these two closed and here the convex set we are considering is not just only convex, it's much close as well. So that's why taking the closure of the sum of these two convex functions here become a H convex function again. So this recover, this is similar to the property we have in convex standard case. And then from this property, this is equivalent to this property, and then this property imply the sum rule. Okay, so this is about the space. So now we go further in a specific example. The first, so consider these three simple functions. And it turned out that they are H-convex as well. And then you can see that I can support these functions by the quadratic functions. And then what I do next is I find the conjugate functions of them, and they are easily calculated. And then I define, and then the minimizations problem, minimization of the sum of these three functions has a dual problem like this. I have the figure of, this one is the figure of a sum of the three functions. And this one is a dual function, these are dual problem. So if you look at the dual problem, you can see that they are actually in R3. So in 3 dimensions. So I couldn't draw 3 dimensions in the hyperplane. So that's why I just consider them in the feasible set. So this is a feasible set. So you can see that they are actually have a zero duality gap. Okay. So how to check? So I will employ one of these many conditions I have. So which is so I check, so conditions here. So this is this condition, sorry. This is these conditions. I found a point X, so that 0 belongs to the sum of the subdifferential. So that X here is 1 and minus 1. And then it's implied that 1 and minus 1 are the solution of the Primal minimization problem as well. So this talk based on a manuscript with Regina, Alex, and David. And abstract convexity is a very interesting field, and it's a rich field that cover many, that has many applications in function analysis and other field as well. If you want to know more about abstract convexity, I recommend the book of Alex Rubinov, which have a discussion on global optimization, and also another book with Ivan Singer on abstract convex analysis. So thank you very much for your attention.
Thank you, Hua. Great presentation, and I would say that it was pretty clear, much clearer than what I was reading. Of course, many applause, and Regina has already started applauding. The others are going to start applauding very soon, I believe. So question time. Are there any questions to the speaker? While people are thinking about asking questions, I want to mention that I was strongly envious during the presentation, looking at how professionally Hua was writing on the screen, using these online tools available. Possibly everybody was thinking about it. So we have a question from Juan Enrique. Juan Enrique, please.
Hello. Well, first of all, I want to say that I like the talk. The topic is very important and old, as you said, because you mentioned these old books by Alex Rubinov and Ivan Singer. But in spite of being old, it is becoming more important in recent times because it's finding new applications. For instance, abstract convexity is proved to be very useful in the study of transportation theory, the theory of optimal transport, just to give a very recent example. But I have a minor comment because I think one of the examples you presented was not fully correct. I may be wrong, so I apologize beforehand if I am making a mistake. No, it's the example where the elementary or the abstract affine functions are quadratic. Yeah. Because you quadratic forms and then a vertical shift. Yeah. No, but in several variables. I mentioned, I mean, the example you mentioned at the very beginning of your lecture. Yeah, it was around. Yeah, exactly. So if you look at these elementary functions which are in calligraphic age, each of them is even with respect to each variable. I mean, if you change xi with minus xi, then the function does not change. And then the same would happen when you take suprema. This means that an abstract convex function, among other conditions, must be even in each variable. So it cannot be true what you said, that every lower semi-continuous function which is bounded from below is abstract convex. But I think the correction is easy. Instead of taking quadratic forms, you take quadratic functions. You add a linear term.
Yes, yes. So yeah, so you are totally correct. So first of all, these two examples are different. So this is example 1, is example 2. They are different. Sorry, they are different affine space, different abstract space. So for this example, we have this one is actually the linear function. This one is a linear function. So this one is a quadratic term, and this one is a linear function. So as you said, so instead of adding, so as you said, instead of considering this, I add another linear term, and then that become a quadratic function with a linear term as well. And then with
this example was studied long ago, more than 40 years ago, by two people. I don't remember who one was the first. One was Balder from the Netherlands, and the other was Duality from Poland, who is now in France. So they published 2 papers in which they included these examples.
Okay.
In fact, okay, bounded from below is a sufficient condition, but a necessary and sufficient condition, if I remember well, is the function to be bounded from below by a quadratic function.
Yes, So by any element in this L.
Exactly. Okay, this was my comment, and congratulations for the nice talk.
Thank you.
In fact, there were plenty of publications, maybe about 40 years ago, from this Polish school of Simon Dalecki and a few other people. Anyway, we have a few more questions, and Andrew Berhard, please.
Oh, hi. Yeah, thanks. Thanks for the talk, Howard. That's great. Just one question. Your conditions for the sum rule, you've got some in terms of just the conjugates of the constituent functions. Does that mean that the rule you have can be applied to, say, the case where one of the functions is not closed in the topology that you're talking about? I'm just wondering, because a lot of in convex analysis, when you have these fuzzy sum rules, they're usually assuming the constituent functions are talking about are closed functions, and I'm just wondering whether, given that you've got conditions that seem to involve just conjugation, which kind of closes things off anyhow, does that imply that? Or, I mean, is this generalizing in a sense the convex cases?
So first of all, for these standard convex functions, we have the sum here. So even if they are closed, but the sum of them is not, summation of them is not closed. So that's why we need this. So that's why this equality not only hold, because in the right hand side, this set is only closed because it's an epigraph of the conjugate, but the sum of two is not really. For this for this theorem, we don't assume that these two functions are convex. That can be any non-convex functions. So in general, not even H convex.
Because you did impose a topology on the abstract convex functions, didn't you? And so therefore, you do have a concept of things being closed or not closed. Yeah. Because I know when I've seen examples like this in the convex case, this rule holds, I know, under some conditions where they also assume F and G are lower semi-continuous functions as well. Yeah.
So, but one of my concern is that because when the function is not convex, then there will be an X so that the differential is empty. The subdifferential is empty. That's why that's highly likely that this sum will be empty. Then how can this?
But the epsilon subdifferentials can be non-empty without closeness.
What? Okay. Yeah. Okay.
I don't know. It's just a question. It'd be interesting to know whether, in fact, these results, in some sense, generalize in the case of convex functions in any way. The convex case. I mean, it's just I'm just wondering. I don't know, looking at it myself, whether you can drop any lower semi-continuity in the convex case on any function. But if they did, then that would be something that I hadn't seen before. Anyhow, that's just so we don't have to resolve that now. Just one other comment. Some years ago, when I played around with some abstract convexity, one thing I observed was that because the Toland-Singer formula for the difference of the conjugate of a difference of two functions holds very generally, in fact, in the case of abstract convexity with very few assumptions, one can also look at the subdifferential of difference of two functions in this context. I'm just wondering whether that wouldn't be a worthwhile secondary problem to look at, given those formulas also exist and generalize quite freely to this context. That's just a comment. It's something I observed, something worthwhile having a look at.
Okay, thank you, Andrew.
Okay, thank you.
And now, Renier, please.
Hi, thank you very much for the very nice talk. This is a very interesting topic. I would like to, my question was a little bit touched in the last talk, in the last question. I would like to know if there is proven or not, or there is some results about when the function is abstract convex, the subdifferential is always not empty. And when the subdifferential is not empty, it is still a maximum monotone.
So the maximum monotone is the maximum monotone. I think Regina is the best person to answer this question.
Yeah, yeah, sure.
She has a result on this.
It's a good trick to pass the question to someone else.
But it is always no empty when the function is convex, is abstract convex.
No, it's not.
With epsilon.
Sorry. Maybe, Rainier, I can tell you that monotonicity or maximal monotonicity can be written in terms of abstract convexity, but most of the concepts like maximal monotonicity cannot be extended in a simple way. There is a paper by Alex Rubinoff and myself in which we study the properties, and even we extend enlargements of maximal monotone operators using that. And if you are interested, I can send it to you. And in fact, I think that your question is very interesting, because this is how abstract convexity can lead us to new, more interesting, to new ways within functional analysis.
Good. Thank you. I will appreciate a lot if you can send me, please.
Yes, I will.
It's a very, very interesting topic.
For your first questions,
yeah.
No. So even if it is not H convex functions, then they're highly likely that there will be a point. There are points so that the subdifferential is empty at that point.
Even when it is a H convex.
Yes, so this one is an example. This one has subdifferential is empty at this point 0, and that H convex even. So
that's good. Yeah.
So it's already very good to see numerous connections, and of course, thanks to questions raised today. Maybe Hua will look at other possible connections, but even the main topic of today's presentation, connection between abstract convexity and optimization, this duality gap, probably Hua could talk a little bit more about the role of this duality gap in optimization. But there are plenty of optimizers in the audience, and probably people understand what it is about. Anyway, do we have more questions? We still have a few minutes left, 5 minutes to be precise, and we have time for 1 or 2 more questions, please. Regina, please.
Your talk was very amazing about the meaning of what does it mean function to be differentiable? Because, for example, you showed us this very nice example of -2 times the modulus, and that the only place where that function is not differentiable in the classical sense is 0. And apparently, even for your general example in which you approximate the function with quadratics, it also gives us an idea that the function is only differentiable outside 0, because only at points which are different than 0 you can draw, let's say, a generalization of a tangent line. So it would be nice to see if what it means to have like a Taylor development in the framework of abstract convexity.
Yeah. Yes. So yeah, I think different derivative is going to be the next step to be able to have a good computation. And for this,
to have computations, exactly,
Who
and
into the microphone, please.
And approximations, because what is being differentiable is being able for you to approximate a function by a linear function, let's say, or by an affine function at a point. So you have a point of contact, and the more contact you have, the more level of differentiability you can have. So can we even develop a theory of approximation using abstract convexity concept?
Yeah, that would be very great. Yeah, that
Okay,
would be
I suspect that probably Hua could come up with some definition of abstract linear or abstract affine functions to make even negative absolute value differentiable at 0. But it will be probably the next step. At the moment, we have a question from Guayin. Guayin, please.
Oh, thank you. I'm not sure you can hear me.
We can hear you very well. We can't see you, but we can hear you.
I was trying to see, because I remember there's a epigraph sum formula for possibly infinite many functions. I was wondering whether there's an analog in that setting for the abstract convex cases.
Oh.
So basically, I'm trying to see whether it is possible, or is it trivial to extend it to possibly infinite many functions? Because then we can talk about maybe problem like semi-infinite program in that case.
Yes. So it's actually, this is in our to-do list after this this work. So we would want to do many things. So one of the things is to extend to infinite. Yeah, but like, can I have a question back to you?
Okay. So, why is getting trickier and trickier?
I mean, yeah, but I tried to think about a way to extend this. But do you have any idea? Like,
I haven't sure, because I haven't played around too much with the abstract convexity yet. But I do know that there's a few. I mean, I remember, for example, Marco has a few very good publication along this line. I think I started with my supervisor try to do the epigraphical conjugate form for the infinite cases, but I haven't done that for this day, so I don't know whether it's still how this link to abstract convexity is not something I know at this moment. Okay. But I think maybe it's of some interest, I would think.
Thank you very much for your comment.
So your to-do list is growing. Eva, please. First, welcome from Europe. Eva, your word. your question, comment? We can't hear you. You are probably muted. Eva? So hopefully we will hear something from Eva. In the meantime, it's already 6 o'clock. It's time to close. And while Eva is trying to unmute herself, just a reminder for everybody that we have another talk in a week. And please come again, keep coming. In fact, we have a big list of presentations coming. So Eva, are you available? Okay. Also, things are coming. And okay, so we still don't hear from Eva, which is a pity. Probably Eva will ask your question by email directly to her. So thanks to everybody for coming to this talk. Many thanks to the speaker who did very well today. And we are looking forward to her next presentation at this seminar. In the meantime, applause to the speaker. So, thank you, everybody, and see all of you next week.